far we have seen different ways in which we can represent a switching function. We looked at the truth table, we looked at various algebraic forms like the sum of product, the product of sum and so on. Now, over the next few lectures we shall be looking at some of the, you can say, unconventional, but very effective ways of representing switching functions which have many applications. So, in many applications we do not represent a function just by a truth table or by an expression, but by using one of these representations that we shall be discussing. Now, the first such representation we shall be discussing is called binary decision diagram. So, this is the first part of our lecture. Let us try to understand first what is a binary decision diagram. So, as you can see from here, from this slide, binary decision diagram, in short we refer to as BDD, is essentially a data structure, we call it, a way to represent some information, to represent a switching function or a Boolean function. BDD is nothing but some kind of a graph. Now, for those of you who are not familiar with graph, let me give you a brief introduction to a graph. So, you see, when you refer to a graph essentially consists of a set of vertices and a set of edges. So, an example graph is, these are the vertices, typically they are represented by circles and there are edges. These edges can connect circles. Now, there are many applications where you can represent the information as a graph. Let us say the circles can indicate some cities or towns and these lines can indicate the roads that are connecting them, right. So, these edges can also have some labels. For example, in the example I cited, the distance in kilometers can be the label of the edges, right, like this and so on. And there are some graphs where these edges can have directions, like some of the roads may be one way roads, right. So, you cannot drive in both directions. So, such a graph is called a directed graph. Now, there is another term which we use, is called an acyclic graph. See, a cycle in a graph means something like this. Suppose I have a graph. So, let us add directions to the edges. So, you see there is some kind of a cycle like this. There is a directed edge. If you consider these 4 edges together, starting from this vertex A, I can go to B, I can go to C, I can go to D, then I come back to A. This is a cycle. Now, an acyclic graph is one where there is no cycle, right. Now, a special type of a graph is called a tree, which is of course acyclic, and a tree looks like this. So, I am just giving an example of a tree. This tree does not have any cycle and these edges can have directions, again may not have direction, and there is one special node which is referred to as the root, which is considered to be at the top of the tree, right. So, these are some definitions or concepts that we shall be using in our definition of a binary decision diagram. Now, let us see. Binary decision diagram is an acyclic graph, there are no cycles, the edges are directed. Well, we may not be showing the arrows in the diagrams, but as a matter of convention, so any edge that connects a node which is on the top to a node at the bottom will be assumed to have a direction like this, top to bottom, and there will be a special node which will be designated as rooted node. Now, the vertices can be of two types in a BDD. So, here we shall be seeing the example. Some vertices are called decision nodes, some vertices are called terminal nodes. Now, the terminal nodes are marked as 0 and 1. There is one terminal node called 0, there is one terminal node called 1. There can be several such. These are called 0 terminal and 1 terminal. They indicate the logic value 0 and the logic value 1. Talking about the decision node, a decision node looks like this. A decision node is labeled by a Boolean variable. Let us say I have a variable a. So, the vertex, the decision node will be labeled by a, and there will be two child nodes. Well, the nodes that connect to it below, they are called child. This is called the parent. So, there can be two child nodes, let us say one here and one here. So, I am showing two different kind of edges, one showed as dotted and one showed as solid. So, the left one I call it as the low child, the right one I call it as the high child. This is the convention. It has two child, every decision node will be labeled with a variable a and will be having two childs, left and right. Left indicates the dotted line, right indicates the solid line. They are called low child and high child, and low child and high child actually indicates. So, we will be going to the left direction whenever a is equal to 0 and we will be going to the right direction whenever a equal to 1. So, the edge, the two edges represent the assignment of the variable here a to either 0 or 1. Now, this we shall see later. So, in a BDD we will be having several such nodes, they will be labeled with variables. Now, if starting from the root, there is a special node called the root. So, if you look at the different decision nodes that come in between, so if the variables appear in the same order in whatever path we traverse from the root, then we say that it is an ordered BDD, ordered binary decision diagram. This we shall see later. Okay. Let us now look at how a binary decision diagram looks like. Well, here we consider a 3 variable function represented by a truth table like this. So, you see these are the output 1 0 0 1 0 0 1 1 and A B C are the 3 variables. Now, this is a classic kind of a binary decision diagram where the root node is on top, this is the root, and the root indicates the function f. Okay. Now, I have two paths left and right. So, A will be having a low child and a high child. This corresponds to A equal to 0, this corresponds to A equal to 1. Similarly, at the next level I have nodes which are marked by B. So, on the left this indicates B equal to 0, this indicates B equal to 1, this also is B equal to 0, B equal to 1, and similarly at the lowest level there are nodes marked C. Similarly, they will indicate the values of C equal to 0 and 1. Like this. So, now you see, starting from the root, if you traverse along any path, for example, if I traverse the leftmost path, I traverse the edges A equal to 0, B equal to 0, C equal to 0, I arrive at the terminal node 1. This corresponds to the first row of the truth table, 0 0 0, output is 1. So, you consider one case where the output is 1 again, let us say 0 1 1, 0 1 1, I come here. Let us take a 0 case, let us consider this 1 0 1, 1 0 1. So, you see essentially what we do here is that if we look into the output column of the truth table 1 0 0 1 0 0 1 1, we simply copy this as the terminal nodes at the lowest level. This will give us one representation for this function. This is what we refer to as the binary decision diagram. Now, one problem with this representation is that because the size of the truth table is exponential for an n variable function, the number of rows is 2 to the power n. Because of the same reason, the number of terminal nodes here will also be 2 to the power n. So, this size of this binary decision diagram will be exponential in size, exponential in n. So, it is pretty large. So, we shall see that there exists some techniques using which we can reduce the size of the binary decision diagram. So, it need not be exponential in size, we can reduce the size of the BDD to a great extent. We shall see some examples in this regard. Okay. Let us move on. All right. Earlier we talked about the Shannon's decomposition theorem. So, we again revisit that same thing, Shannon's expansion we are calling here of a function. Now, the idea here is that we can construct a BDD from a given function by repeated applications of the Shannon's decomposition theorem or Shannon's expansion theorem. Now, recall earlier when we talked about the multiplexer realization of a function representing a function using 2 to 1 multiplexers, there also we did the same thing. We successively decomposed a function into sub functions by applying the Shannon's decomposition theorem. We got smaller and smaller functions, and every decomposition was mapped to a 2 to 1 multiplexer. Here the concept is almost identical. Every decomposition will be corresponding to one decision node of the BDD, and we repeatedly do it, we get the complete BDD. Let us see. Take an example. Suppose I have an n variable function f, the variables are x1 to xn, in general there is a variable xi. So, we talked about this earlier also. So, we defined something called a positive cofactor. This we denote as fi with 1 in the superscript, which means the same function where this xi is replaced by 1. This is referred to as the positive cofactor with respect to variable I. So, in the same way we can define a negative cofactor. Negative cofactor is very similar, which is denoted by fi 0, where this variable xi is replaced by the constant value 0, right. Now, Shannon's expansion theorem we have already seen. Now, here we are showing two forms of expansion, one of that we have seen earlier. So, in Shannon's expansion theorem we can write the function f like this. So, when you expand a function with respect to x, I can write xi dash, that means the complement of xi, multiplied by the negative cofactor with respect to xi plus the variable xi and the positive cofactor. Now, there is an alternate representation also which we have not talked about earlier, where this is something like product of sums. The same function we can write like xi plus fi 0 and xi bar plus fi 1, but of course, we shall be using the first representation only in our examples and illustrations. Now, one thing you see, the way we expanded here this one, so we can map it into a decision node of the BDD, where the node will be labeled by xi and the left and right, this corresponds to xi equal to 0, this corresponds to xi equal to 1, the low and right childs, they will be corresponding to f I 0 and f I 1. So, basically, and this of course, this will represent the function f. So, every decomposition of the Shannon expansion can be mapped into a decision node of the BDD or a decision vertex. This is the basic idea. So, function example here, consider a 3 variable function like this. Here in this step we are decomposing this function with respect to the variable a. So, we write a bar multiplied by the negative cofactor, replace a by 0, you get b bar c bar and b c, plus a multiplied by the positive cofactor, replace a by 1, this becomes 0, c plus b c. Now, c plus b c can be simplified into only c, and this cannot be simplified any further. So, this decomposition, as I said, can be conceptually mapped into a decision node, where this node is labeled a, the low child refers to this function b bar c bar plus b c, and the right child refers to this function c. Okay. This is of course the first step, and we repeatedly go through this. Next we will be doing, let us say, using variable b, next we will be doing using variable c, and so on. Let us see how we do it. Well, here the whole step is shown. The first step we have already seen, this step we have already seen in the previous slide. So, where we have expanded the function with respect to variable a, and we have got two sub functions b bar c bar plus b c and only c. In the next step, let us suppose we are trying to expand with respect to b. So, this b bar c bar plus b c, if you do a Shannon expansion with respect to b, you do it in a similar way, b bar multiplied by the negative cofactor with respect to b, replace b with 0, this becomes 0, it becomes only c bar, and b multiplied by positive cofactor, replace b by 1, it becomes only c, right. Similarly, for this variable c, you do the same thing with respect to b, b bar multiplied by replace b by 0, there is no b, so it remains c, b into positive cofactor, replace b by 1, no b, so it remains c. And in the last step, you expand, you see now we have got 4 sub functions c bar, c, c and c bar. So, you see the size of the sub functions are getting smaller and smaller as we proceed. So, in the last step we expand by c, you see c bar can be written like this, c bar multiplied by the negative cofactor, replace c by 0, it becomes 1, plus c negative the positive cofactor, replace c by 1, c bar becomes 0, right. But if it is c, then c bar multiplied by replace c by 0, it is 0, c into replace c by 1, it is 1. So, in this way I get this. Now, you recall when you do the expansion, here I have shown a, b, c, I can do it in any order. I can first use b, then a, then c, or I can use first c, then a, then b, and so on. So, here I have illustrated only one particular order, the variable ordering is a, b, c. So, at the end I get some constants or terminals, you see 1 0 0 1 0 1 0 1, remember this 1 0 0 1 0 1 0 1. So, I can directly map this into a BDD like this 1 0 0 1 0 1 0 1. So, my order of expansion was, first I used variable a, next level I used variable c, third level I used variable c, b and c, right. This is how we had carried out the expansion. Let us take another example, let us work this out. Suppose we have a function like this, A bar B C plus B bar C bar plus A C. Let us follow some particular order, not necessarily A B C. Let us say first we expand with respect to variable C. Let us see. So, it will be, the function will be C bar, the negative cofactor, replace C by 0, this will become 0, it will be B bar or A, B bar or A, B bar or A, plus C into, replace C by 1, the last two will become 0, it will become only A bar B, A bar B. So, I have got two sub functions B bar plus A and A bar B. In the next step, let us expand with respect to A, let us say. So, this function, if we expand with respect to A, this will be A bar into, replace A by 0, it will be only B bar, plus A into, replace A by 1, this will be something plus 1, it will be 1, right. In the same way, if you expand this with respect to A, it will be A bar, replace A by 0, so it will be only B, plus A, replace A by 1, this will be 0. So, now you have 4 sub functions B bar 1, B and 0. Now, we are left with B, okay. We will be expanding with respect to B. So, B bar can be expanded as B bar, replace B by 0, this will be 1, plus B, replace B by 1, this will be 0. And here we have a constant 1, okay. So, if you expand by B, B bar, replace B by 0, there is no B, this remains 1, plus B into, replace B by 1, it remains 1. And for B, it will be B bar, replace B by 0, this will be 0, plus B, replace B by 1, this will be 1. And for 0, this will be B bar into 0 plus B into 0. So, now we have 1 0 1 1 0 0 0 0. So, now our BDD will look like this. We will be having the root node C at the top level, this will represent the function f. At the next level, we will be having A and A. This will be the negative edge 0 and this is the positive edge. Next level, we will be having B, 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 B and B. So, this will be negative, this will be positive, this will be negative, this will be positive. And at the last level, we will be having C, no, not C, okay, C, A, B, you have taken all. So, last level you have the terminal nodes, okay. So, if you take the terminal nodes, so you have 1 and 0. So, you will be having 1 out here, 0 out here like this, then 1 and 1, 1 out here, 1 out here like this, 0 and 1, 0 out here, 1 out here and 0 0. So, you have obtained the binary decision diagram for this function. So, given any variable ordering, you can construct the BDD by systematically decomposing the function using Shannon's law. Okay? Fine. Now, let us talk about variable ordering. The point to note here is that the size of a binary decision diagram is determined not only by the function you want to represent, but greatly also on the ordering of the variables. You see, in general, for most of the functions, BDD gives a very compact representation for a function. We shall see some examples later. But what we are trying to point out here is that the ordering of the variable plays a great role. We shall take an example where the ordering, if we change, the size of the BDD can differ to a great extent. Well, of course, here we shall be showing you the reduced or minimized form of BDD, which we have not discussed so far. Just we shall be showing you pictorially how the reduced version looks like. Later on we shall see how to arrive at the reduced version. Let us see, let us take an example. We say that it can be proportional to the input variables, it can be proportional to the power of an input variable, it is called exponential. Let us take an example. This is a very classic example. Suppose I have a function which looks like this, where the variables are paired, the product terms are like this x1, x2 or x3, x4 or x5, x6 like this. So, if I use expansion, if I use variable orderings like this, first I choose the odd numbered variables x1, x3, x5 and so on, then I choose the even number of variables, then it can be shown that I will be requiring exponential number of nodes in the reduced or minimum BDD representation. But if we use a variable ordering which is just x1, x2, x3, x4 in that order, then we will be requiring only 2n nodes. This is a very classical example which is given in all textbooks, which is used to show that variable ordering is very important. Okay. 2 to the power n is very large, it grows very quickly with respect to n, but 2n is proportional to n. Okay. Let us take a very specific case of that function where there are 8 variables. So, x1, x2, x3, x4, x5, x6 and x7, x8. First we consider the bad variable ordering, that means we expand with respect to this, first the odd number of variables x1, x3, x5, x7, then the even number variable x2, x4, x6 and x8. So, you see here the entire BDD is shown. Of course, this is not the conventional BDD, this is the reduced version of the BDD. So, we shall see later how to reduce a BDD in size. But the point to note is that you see there are large number of nodes in this representation. If you count how many 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 23, 27, 29, 30 and 2 terminal nodes. Total 32 nodes are there in the BDD representation if you have a variable ordering like this, right. But this same function, if we use an alternate variable ordering, like here the same function we are using a variable ordering like this x1, then x2, then x3, then x4, then x5, x6, x7 and x8, then we have, you see, such a compact representation of the function where the number of nodes are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, only 10 nodes are there. So, this is a very classic example which is used to illustrate that the ordering of the variable is very important, and most of the BDD generation and manipulation tools, they try to find out a very good ordering of the variables so as to minimize or reduce the size of the function. So, the important point to note is that just I mentioned this just now, that it is very important to find a good variable ordering, and we have a binary addition diagram here which is called ordered binary addition diagram, where the ordering of the variable is defined. Of course, finding the best ordering is not easy. This NP hard is a class of problems which are considered to be computationally very complex. Why? If there are n number of variables, the number of possible orderings can be factorial n, and factorial function grows very rapidly with n, right. That is why this is a very difficult problem. But there are a number of rules or heuristics, these are called, which are used to find a good variable ordering in general. So, with this we come to the end of this lecture. Now, in the next lecture we shall be looking at how we can reduce the size of the BDD to the form in the two examples that we showed. The conventional BDD looks like a tree, how we can reduce the size of the tree and make the BDD more compact. Such rules we shall be discussing in our next lecture. Thank you.